asking, consider a CG amplifier loaded in a resistance RL is equal to RO and fed with a signal source having a resistance Rsig is equal to RO divided by 2. Also let CL is equal to CGS. Use the method of open circuit time constant to show that for gmro much greater than 1, the upper 3 decibel frequency is related to the Mosfet Ft by the approximated expression of Fh is equal to Ft divided by gmro. Okay, so here the question is asking us to prove this one. We have to prove that Fh is equal to Ft divided by gmro when RL is equal to RO and Rsig is equal to RO divided by 2, and when CL is equal to CGS. Here we are going to use the open circuit time constant method to do this. Okay, first of all, let's look at the circuit. Here we are dealing with the common amplifier circuit. So the diagram for the common amplifier look like this. We have two capacitance. One is CGD, that is gate to drain capacitance right here, and then here this one will be grounded right here, and then this is CGS, that is gate to source capacitance, and then here we have the Rsig resistance, and then here we have the Vsig resistance, Vsig voltage, Vsig, and then this is the gate. This is the gate of the Mosfet connected to this. So Mosfet right here. Okay, and here we will have the RO resistance, and here we have the load resistance RL. Okay, this is the output voltage, and this is how the diagram of the common gate amplifier look like. And this one here is 1 over gm and all the stuff. And we can also draw the small signal equivalent model of this one by considering Rsig is equal to RO divided by 2, which is mentioned in the question. And also what else provided, they also mentioned that RL is equal to RO. Considering all that, we can also draw the small signal equivalent model of this. That one look like this. Here we have the Vsig voltage right here, and then instead of Rsig we put RO divided by 2, and this one is source, and then here we have RO resistance, and then the current source right here is the GM VGS, and this one connected to the drain, and we will have the capacitance in parallel CL right here, and CL is parallel with the CGD. And this one also parallel to the RO resistance. Here we are considering the load resistance as RO as well, because they mentioned that RL is equal to RO. So by considering that, we can draw like this, the small signal equivalent model, and this is the gate, and this one connect to the ground. Okay, so when we do the time constant method, what we do is we open circuit. When we considering the circuit, we open circuit both of this capacitor and then find the time constant. So if you do that, then the diagram will look like this. We are going to have the exact same diagram, but these two capacitors will be open, and there we will calculate the time constant. So what I can do is I can just copy this diagram right here. Copy this diagram, and so let's call this diagram as figure 1. This is figure 1, and let's call this a small signal equivalent model as figure 2. And then for the open circuit time constant, we bring the exact figure 1 right here, but this time what we do is we just open the capacitors. So the last new picture is going to look like this. Let me get rid of this. So we have to just open this one, CGD and CGS, and here we will have the time constant. Okay, so this is the equivalent model, and then here by looking at this we can say that, and also we have to know one thing, that RGS is faced in this way. It's the gate to source resistance, and this is RGS, and then here we will have the input resistance RA. And if you look at RGS is nothing but Rsig, this resistance right here, that one parallel to the input resistance, that's Ri. So by looking at the first, we have to look at what is Ri, but by looking at the figure, let's call this one figure 1 and 3, figure 3. This is figure 3, and in the figure 1 we had the same thing with capacitors on. And by looking at the figure 1 and figure 3, we can find out the expression for the Ri, which is Ri is equal to 1 over Gm. This one is 1 over Gm right here. 1 over Gm plus the load resistance RL divided by 1 plus gmro. Okay, and if we combine them, this is going to become RL plus RO divided by 1 plus gmro. And also in the question they mentioned that this gmro is much larger than 1, so whenever we see 1 or something close to it, we can neglect that. So which means this 1 is unnecessary. It's like, think about a big number. If you're adding 1 million to 1 million, you can just neglect and say 1 million, right? So like that, this one is negligible, so we can say this one is approximately RL plus RO divided by gmro. Okay, and RL is equal to RO as mentioned in the question. They have said that RL is equal to RO, then which means this is also RO, then RO plus RO divided by gmro, which is 2RO divided by gmro. So let's bring it to the next page. So this input resistance is nothing but 2RO over gmro, and here RO cancels, then this becomes 2 over gm, and that is the input resistance. And we are interested in finding the RGS. RGS is Rsig parallel to the R input, that's why we found out the input resistance expression. Now we have the input resistance expression, and they have also mentioned that this Rsig is equal to RO divided by 2. So we can, instead of this, if we look at this expression right here, instead of this Rsig, I can put RO divided by 2 as well. So let's bring the expression again. As we seen before, RGS is nothing but Rsig parallel to Ri, and we just found out Ri to be 2 over Gm, and Rsig is, as mentioned in the question, that is RO divided by 2. So RO divided by 2 parallel with 2 over Gm, and when we have parallel resistance, the equivalent resistance is product over sum. So you have to just multiply and add both of them in the denominator. So if you do that, you will get 2RO divided by 4 plus gmro, and they have mentioned that this gmro is much larger than 1, which means 4 also is much larger than 4 as well, because 4 is close to 1. So you can neglect this 4, and then we can also mention here, since gmro is right in a better way. Since gmro is much larger than 1, we can say this is 2ro over gmro. Then here also 2 ro cancel, so this one become 2 over gm. So this is our RGS expression. And what else we need? Now here we are going to find everything using the time constant method. So we have to know the relation of the time constant equation. The time constant equation is this: the tau h, which is RGS times CGS, plus the load capacitance CL plus CGD, the gate to drain capacitance, times the RST, source to drain resistance. Okay, and this time constant method is this time constant equation is helpful for us because here we are looking at the 3 decibel frequency. We have to find out this expression. In order to find this one out, we can use the open circuit time constant method. In open circuit time constant method, that omega h is equal to 1 over tau h, and this omega h is nothing but 2 phi fh, and that which is equal to 1 over tau h, and this fh is the 3 decibel frequency. That's what we are interested in finding, and that is equal to 1 over 2 phi tau h. Okay, so here we have the expression for the tau h, that is RGS CGS times CL plus CGD times the RST. So we have to just plug it in this equation and solve for this. Okay. What else we have to know? So source to drain. Source to drain. So R, and also we have to know that RST and RGD is going to be equal as well, because since RL is equal to RO, both of the resistance are going to be equal. So we, instead of RST, we can also say RGD as well. So this expression we can express as 1 over 2 phi, and then we bring in all the values, that is RGS times CGS plus CL plus CGD times RGD. Okay, so this is the expression. Now let's see what we can do for this. Okay, first we have what we found out here is RGS. So we have one expression for the RGS. We have to find an expression for the RGD. For the expression RGD is nothing but gate to drain resistance, which is gmro times Okay, let's look at this. RGD is gmro times RO divided by 2 parallel RO, and that is product over sum, and if you simplify this one, you will end up having gmro times ro divided by 2 multiplied by ro divided by gmro ro divided by 2 plus ro. And as we seen before, since gmro is much larger than 1, we can neglect any value that is added with gmro. So which means we can eliminate this ro right here. So this will become gmro times ro divided by 2 times ro divided by gmro times ro divided by 2 times nothing times the plus ro that can be eliminated by comparing this gmro value is much larger. So this gmro ro divided by 2 ro divided by cancels, so we get the rgd value to be ro. Okay, so this is one conclusion. So now we have something to write for rgd in this expression. Instead of rgd we can just put ro right here. Instead of rgs we can put 2 over gm. Okay, so what else we need to do? We need anything else here? Nothing else. So we can plug it in the equation and see what's happening, right? So let's deal with omega h first. Omega h is nothing but 1 over tau h, and 1 over tau h is the whole expression we had right here. This tau h is the rgs times cgs plus cl plus cgd times rgd. So rgs times cgs plus cl plus cgd times rgd, cl plus cgd times rgd. Okay, now instead of rgs we can put 2 over gm, and here also mention that cl is equal to cgs. So instead of cl we can put cgs. Instead of rgs we can put 2 over gm. And what else we can do? Instead of rgd we can put ro, because we solve rgd to be ro. So doing all that, this equation is going to look like this: 2 over gm times cgs plus, instead of cl we can put cgs because in the question that mentions cl is equal to cgs. So instead of cl we put cgs right here, and instead of cgd we put where am I? Instead of cgd, instead of cl we put cgs, cgd we keep it as it is, and rgd is the one we found out to be ro. So we put ro for this, and let's try to simplify this form. So 1 over this one, 2 over gm here. What we can do is we can multiply this ro for both of them, cgd and cgs, and then take the cgs common, because if we multiply this one, this is going to become cgs ro. Then if I take cgs common, then this one become 2 plus gmro over gm, and then the last one multiplied by cgd ro remain the same, cgd times ro. Okay, and here what else we can do? And also we know that gmro is much larger than 1, so if anything added with gmro we can eliminate it. So here these two added with gmro can be eliminated by saying, since gmro is much larger than 1, so here we can say since gmro is much larger than 1, we can say that this omega h is nothing but 1 over cgs gmro over gm, 1 over cgs gmro over gm times not times plus cgdro, and here gm cancels, so which means this is 1 over cgsro plus cgdro. Okay, so this one seems to be, this one looks very simple, and this omega h is nothing but 2 phi fh, so we are interested in fh, so this 2 phi come in the denominator, and then here also we can take the ro common. If we do that, then this one becomes cgs plus, this is cgd right here, cgs plus cgd. Okay, and there's another thing we have to know, that there's also a frequency ft that is expressed as gm over 2 phi times cgs plus cgd. Okay, and if we bring this 2 phi cgs plus cgd term in the other side of the equation, two phi, okay, this is f small t, ft, capital T, and if I bring this 2 phi cgs cgd term to the other side of the equation, cgs plus cgd the other side of the equation, in the opposite side gm over ft. This equation is useful for us because if you look at the fh equation we derived, we have a term that is 2 phi cgs cgd right here in the denominator. Instead of that 2 phi cgs plus cgd expression, we can substitute this gm over ft. In that way we can bring similar to this one, because they ask us to prove how did we derive this. This is how this ft equation is helpful to do that. So here now I bring the fh equation back, so fh, and then I'm comparing this. So here 1 over 2 phi cgs plus cgd, instead of 2 phi cgs plus cgd I put gm over ft, but there's one extra term, that is ro still remains, so this is going to be 1 over ro times gm over ft. Okay, and this ft divide can be flipped around and put it on the top, so this is going to be ft over gmro. And if you look at the question, that is what they have right here, and that's what they're asking us to prove. And that is it for this question. I hope you guys found this video helpful. Thanks for watching. Don't forget to subscribe my channel. See you guys on my next video.